Right? So let's mute this here. Right. So what I'd ask you all to do is to start looking at another past paper to continue your revision and review. But this morning, before we get there, I wanted to do a little quick review on the sort of last topic that people may have had an issue with, which was convolution. Okay, so I'll talk not so much about going over the whole process again, but about some of the things, just to remind you of what we covered, what we were expected to cover in convolution. And feel free to ask questions on it at any time. All right, and then we'll get around to the past paper and see how you all are making out with your work and so on. So let me share this. Okay, so this particular lecture, we did a couple of lectures on convolution. And just to remind you all, before we get to this, remember this thing about convolution. This is what really happens in a system when you put an input into a real system, whatever that system happens to be. Once you put an input into that system, what really happens is that the system convolves, there's a convolution between the input and the system behavior. For our purposes, remember that this in continuous time descriptions is a differential equation, right? And this is, of course, a continuous time signal. So a continuous time signal going into something that is described by a differential equation, it could be a circuit, right? An ordinary circuit, but the behavior, because it's continuous time, has some differential equation description for it. Whatever output happens is a convolution of the input and the system itself. So this is what happens in reality. What we did is that this is normally for situations other than simple signals and simple systems. This is difficult to evaluate manually. So we came across another tool that allows us to examine that behavior in another domain where this particular convolution became a multiplication. And that was the Laplace domain or the S domain. So that this, if you transformed the whole behavior of the system, you transform the input and you transform the system behavior, that differential equation, then the convolution became a product and you were able to now look and see what the system did in the S domain. And we saw that there's a whole lot of information we could evaluate and gather from that. And then if the system is doing what you want, then you take the inverse transform to come back to real time. What happens is that the operation of the convolution, we at least need to know how it is done mechanically, although we use these for more complicated systems. Because this is what happens real time, we need to at least be able to evaluate a typical sort of behavior in real time. And that is where the discussions on doing the convolution manually came about. And we saw that the process, for instance, if I were to give you an example like what we have here, where you have a signal here and you have a system here, to find a convolution of it, remember the convolution is defined by an integral x tau h t minus tau d tau, and you have to set the limits according to what the particular problem is asking you. And this now, so what you're being asked to do first off is that you take the sort of operation, the steps involved is that you're given ht and xt, then you change the variable from t to some other dummy variable. Why? Because we are integrating with respect to, you can't integrate with respect to the same variable that you are trying to substitute. It's a bit of calculus that you should have remembered or done in either ADMATS or KEEP. But really and truly, it is not, you're not supposed to be able to do something like this, to integrate t squared dt between t1 and t2, right? Because what you're doing, you're integrating a variable, but you're also substituting the variable at the same time. What is supposed to happen is that you're really supposed to integrate a dummy and then substitute the correct variable inside of it. All right, because the limits of the integration and are not supposed to be the same thing as the variables. Excuse me a minute, it's just the office. Yes, right. So that was just a little bit of mathematics. So the first sort of calculus rule that we have to do is that we have to change t from h, the variable, and we in our thing we go from ht to h. Oops, let me get back my here to h tau and to x tau. Now I'm not changing anything. I haven't changed the shape of the signal. I haven't done anything. The next part, if you look at the expression up here, is x tau ht minus tau. So we now have to, if I'm convolving x and ht minus tau, h minus tau is h tau flipped, right? And if you remember, we did some signal manipulations like that. If I give you a signal here, and this is h tau for argument's sake, h minus tau is that flipped around the t equal to 0 line. So h minus tau is going to be this, right? And then if you now say h3 minus tau for argument's sake, what you have done now is to shift this to the point where the h naught, if you look at this, where's h naught? H naught is here, right? So if I flip it around, then h naught is now, let me just get a different color here. The h0 will still be here. h3 minus tau, if I ask you where is the h naught located in terms of this now, it will be at tau equal to 3, right? That will give me my h0 point. So at tau equal to 3 would be somewhere, let's say about here. So h3 minus tau will mean this has been slid, right, to the point where this is now here. You flipped it around, so you now slide this whole thing. So this is now the h, but this is h naught now, right? So you slid it now, and this is where the h naught is. So this is what h3 minus tau is. And we did all of that. We shifted around things to the left and to the right of the axis and so on. But the important thing is always to, if you want to determine which direction to go in, to see what value of this variable makes the 0 point, in other words. Right? Everybody remember that? We okay on that? Yeah, no? Maybe? Right, I think there were some previous slides that spoke about that. Right. right? So like right here, so you start off with the two signals, you change the variable, which doesn't do anything to the signal. And then if h of tau is that, h of tau is the upper one, h minus tau is just you flipped it around this line, the t equal to 0 line, and ht minus tau flips it around. This is the center line here. So this is your sort of, anytime you have ht minus tau, look and see where the t0, this is sort of referring to the t0 point here. So h4 minus tau means that this now has now gone on to the point t1 equal to 4. Okay, if you look at the other, there's tau here, h minus 3 minus tau would have sent it this way to some point minus 3. Okay, so depending on wherever t is the point, the 0 point for the signal. So like, again, if I have a signal looking like this, right, if this is h tau here, and this is going from 0 to 7, h minus tau, right, is going to go from minus 7 to 0, all right, and ht minus tau will be, this is the t point here, because this is the point that is moving up and down. So if I shift it somewhere, t is here, and the back of the thing is 7 less. So it's t minus 7, that's the back of the pulse. Okay? And that's how it is. So you could shift this now. So regardless of what t is, you know where the pulse is located. T in this case, when you flip it around, t is the front of the pulse. So t is anywhere along this axis. And wherever the pulse is located, t, the back of the pulse is 7, because the pulse is 7 units long, is t minus 7. All right? So we did that, and then you just look at where they overlap. And once they overlap, now we integrate between the limits of you find the product of the two signals and you integrate that zone alone. All right? Everybody recalling that? Yeah? No, maybe? Yes? Yes or no? Come on, let me hear. I'm not hearing anything. I'm not seeing anything on the chart. So it's up to you. You have to tell me. Are you following what I'm saying? I just heard something, but it was very soft. Yeah? Akim, you said something? Yeah? Okay, good. Oh, that's very silent, very soft. All right. So once you do that, if you have it, the particular, so like this example that we have here, if I were to, let's just clear some of this a little bit. So this particular one here, if you're trying to find out the convolution, so as we said, this next step, h tau x tau, then h minus tau would be flipped. Notice the 0 is here, so h minus tau is going to go this way, right? This 0 is really for the vertical, it's not drawn well. So this will be 0, and this will be minus 1 here for it. So if I shift this around now, right, let me just draw this. If I were to shift this a little bit, and this was the front of this pulse, the back would be t minus 1. All right, just if you move it. And then we now have to, seeing that we are evaluating the integral of x tau h t minus tau, This one is a one that is sliding, which is this one here, right? So we're shifting t around and we evaluate the integral. So if you were to let me get a different color here. It's a good color to use. We have blue here, so red. Okay. So the sort of zones now. So this is ht minus tau. This is t. This is t minus 1 here. Right? Have a second. Right. So the first zone, so what you do now is to evaluate integrals in zones. So if t, remember this is 0 and this is 2, right? So for t less than 0, there's no overlap. So therefore the convolution is 0. And then the next point is to shift it now. The next zone right is this now. So this is zone 2 now. T minus 1. So this point here is t greater than or equal to 0. And if you look at it, the back of the pulse here is coming up, and t less than 1. Sorry, t minus, what am I talking? And the back, t minus 1 less than 0. Combine the two of them, you have t less than 1 and greater than or equal to 0. So that's the next zone, right? And the zone of overlap, where the two of them overlap, is here. So that the integral limits will be integral between the lower limit 0, the upper limit t, x of tau, which is 1, h of tau, which is also 1, d tau. And you do that and you evaluate it. Right? Now, this brings us to a little observation that you have to make. First off, you always look and see if this signal, oops, I'm making a mistake here. I didn't realize the signal is 2. So this is supposed to be t minus 2. And you all didn't tell me anything about this. Look at the length of this signal here. H is 2 time units long and X is 2 time units long. Always compare the two and see if they are equal or if one is bigger than the other one. All right? And you didn't notice that. This point is supposed to be t minus 2 here. Right? So it's between and t minus 2 less than 0. So t less than 2 and greater than or equal to 0. So as we keep increasing, so you see this overlap zone as ht minus tau moves, the overlap zone will keep getting bigger until we have the situation where h and x are totally overlapped, right? Because both of them in this case happen to be 2 time units in duration. So at that point, so that's the second zone. So the second zone, this is how it varies, and up until t equal just less than 2. Remember, t is the front of the pulse, so the pulse is slowly moving up until it reaches that point. So after that now, right, clear some of this stuff out. right? So the next zone now is going to be just after the overlap now, we have the situation like this now. So this is H, this is your H, T minus tau, keeping moving. So now it keeps moving here. This is the back end, which is T minus 2 behind. So it slid on, the area of overlap started, it got bigger and bigger till one pulse was entirely over the other one. And now it's starting to get less. So the area of overlap is now this. So first thing you need to evaluate the zone. This is 0.2. So this is T greater than or equal to 2 and T minus 2 less than 2, which together gives you T less than 4 greater than or equal to 2. And the area of overlap is this, so that therefore the integral limits will be, the lower limit is T minus 2 and 2, 1 for xt, 1 for h, t minus tau, d tau. Right? And then the last zone, of course, is when the back end of the pulse, remember now this is going to get less and less, so it's overlapping here. This is moving, this is moving, this is moving, so it's keeping doing that as this moves away. And eventually now the back end of this reaches here and then crosses, and at that point, T minus 2 is now greater than or equal to 2, or T greater than or equal to 4, and then there's no overlap. So the convolution is 0, right? So the convolution in a situation where the pulses are the same, the pulses have the same duration, you have one zone with no overlap, right? You have one zone with increasing overlap. You have one zone with decreasing overlap, and then you have another, the last zone with no overlap again. Right? So your answer has to have 4 time zones, right? One with before the convolution starts, 2 during the convolution, and 1 after the convolution. Yeah? And of course, they vary, a couple of variations with this. First off was if the pulse looked like this one. This was a class problem that he had. So the same pulse sizes, the same pulse description, both of them are 2 units long. But this one now is symmetrical about the 0 point. So if you flip it, h minus tau is going to look the same thing, right? H minus tau is the purple here. And if you shift it around now, remember, this is the 0 point here. So if I shift it, this is the point, is going to be the point when I shift this in any direction. The middle of the pulse is t, because it is symmetrical about that point. The middle of the pulse is t, so here the front of the pulse is t plus 1, and the back of the pulse is t minus 1. And you do the convolution the same sort of way. So when you have it here now, this one, the front of the pulse is t plus 1, the back of the pulse is t minus 1. So the limits, of course, would be the no zone, the no overlap zone will be t plus 1 less than 0. And then the 2 overlap zones will be following. And then the last overlap zone will be when the back of the pulse here crosses this unit, the 2 time unit here, right? So the answer will change a little bit. The actual convolution formula, when you work the integral, because you're finding the integral of 1 by 1, because each of these is just a unit, is just a one amplitude unit, well, 1 unit amplitude, then the actual integral part is going to remain the same. It's the limits here that are going to give you some slightly different answers. All right. And then this variation we had here. Okay. So before I get to there now, right? So everybody remember the mechanisms, right? Of course, you did a number of problems on that in the problem sets in class and so on. And the kinds of scenarios that you have to remember now for going through the course were the one where you, okay, so you're convolving two pulses that have the same naught t, naught t, right? That's the first one, is the simplest one. The second is where you have the pulses of different lengths. So you have one going naught to t, and you have one going naught to t1, where t1 is not equal to t. So in this case, you get the convolution. As we say, the convolution has 4 zones: the no zone, the increasing, the decreasing, and the final one. This one has the same sort of behavior. So you will have nothing, then the convolution increases. Then at some point in time, because the pulses are not similar, one of the pulses is going to be totally subsumed, if you like, by the other one. It's going to lie within that range, something like that. And you're going to have a 5th zone in the convolution. So you're going to have the no zone, the no overlap. You're going to you will have an increasing zone. Then you will have a constant zone. Then the decreasing zone, and then the no overlap zone. All right. This is what I was telling you. You watch the pulse lengths first very carefully. If the two are the same, then the answer is going to have 4 parts of the answer. If the pulses are not the same, then the answer will have to have 5 parts. And then we got a little more complex where the pulses now change shape. So you had things like a rectangular pulse and something looking like that, a ramp, right? A rectangular pulse, and then a triangle, and then something looking like this now, 2 triangles, right? We never really did much on this. We got on the last one, because the approach to this is the same as the approach more or less for this one. It's just that the arithmetic and the calculus is a little bit more, and it's not adding anything in terms of trying to see if you understand it or not. What people have an issue with, of course, here is that you have to find the equation of a line, right? And you need to remember that little bit here. So you look at the slope and the intercept, and you try to find it. All right. Here, you have to find 2 lines. So you have to find the equation of this line, and you have to find the equation of this line. Okay. A number of people, like in the midterms and in the problem sets and so on, get stuck on that one. I give you an arbitrary line in the middle of nowhere, but it's easy. You know the gradient, you know the intercept. So that is arithmetics, right? That is CSEC stuff. So you have to try to remember something that you probably didn't do for quite a while, but you have it here. And once you get the equations correct, then the rest is easy. If you're given these 2 things, always remember that x at t convolved with ht is the same as HT convolved with X. It doesn't matter the order. So if you look at these things, they want to flip and slide is always an easier, the easier one to visualize. So like in cases 3 and 4, it's always easier to visualize if this is HT, that this one will be the one that you'll flip and slide. Or if I told you that this was XT and HT here, and I ask you to find the convolution, that the one that you would do would be to flip the X one instead. And so you're evaluating HT XT minus tau d tau instead. Both give you exactly the same answer. It's obviously easier to do it this way than to try and visualize flipping this around. Okay? And then we never, as I said, I never really give you this one because it's just sort of calculus for the sake of calculus. It's not going to, if you can do type 3 or 4, then type 5 is just to see if you could do more maths in the same amount of time, which is not really what I'm trying to get. The learning outcome isn't that. All right. So those were the sort of scenarios, and of course, in all of these cases here, right, the pulse lengths, the pulse or function lengths, time, durations, I should say, may be equal or unequal. If they are equal, then you would have a certain number of zones. All right. If they are not equal, then you're going to have one more zone because of the overlap. The rectangles have 4 and 5 zones. This one similarly will have 4 and 5. These are a little bit different because you have to, it's a discontinuous signal, and we had some examples of that. So you will increase up to this point, and then so you have to evaluate the integrals in 2 parts. There are some questions, in fact, I think on this slide, there's one here that I'd asked people to do when we did this slide as homework, so we could try that. I think we had the problem set. There's a problem set solution to this one, but try it again, right? And of course, the variation for this would have been if I had the, I could do this, right? So that the unit is now 3 units long, and you have a different equation for this side and this side. Of course, because the slopes are now different. And there's, in fact, I think there was a problem set on that, a question on that. All right, so those are the kind of things. Just want to make sure and throw that to make sure they don't forget that that is one of the topics that we revise as well, so that in terms of the coverage inside of what I want to review for summer as well. All right. Okay, so you have that. You have the slides. You have the recordings of the lectures and so on. So if there are any questions on that, let me know. Okay. Right. So the other part now. So let me hear you, back to you a bit now, in terms of your. I had asked you to start looking now at the past paper 20, which one it was, 2011? See, I have it somewhere here. 2011, the 2011 paper, I think it was. Yes, so how many people have started to look at that? Where are we? This one. Okay, wait a minute. You're not seeing it. Hold on. Let's try and see what's happening here. Am I sharing? Do I have something here? How many of you all were able to started to look at it? I'm not hearing you. Yeah. How many of you all have you started to look at this one? It's very straightforward. Again, it's the kind of thing, just quickly, we have the solution. Actually, the solutions don't have question one in it. I have some partial solutions, but that's not a problem. We could talk about that. In terms of your attempting question one, A, that's a straight substitution. So is B. This one is something where a student made a mistake. You can see what that is. This one, we did these sort of questions in class. See? All right, this is a typical example of what we've done here. You're given a response. This one is similar to December's question. And then the Laplace transform. And this is proving a little property of the transform here. And then we have a stability question right here. So this should be fairly straightforward. Have you all started to look at this as yet? I need to know if you're getting stuck anywhere, because the revision now, I've covered the material that I intended to cover, but it's now up to you to tell me if you're getting stuck anywhere. You have the solutions for it. So the issue is that if you still don't understand something, or you try it and you have an answer, but you're not getting the answer that I'm getting, right? And you want some clarification. That's what I need to get from you all. Right? Yeah, so if you all haven't started, I mean, fine, that is not a thing, but we still have to. I just want to, I'm sort of prompting your own coverage now. I've covered all the topics that I think we needed to cover. We went through the course on the material in doing the last past paper. So really and truly, it's study time for you now, study and doing the problems and so on. And less time for me. So my meeting you in class now is really to answer questions that you will have from now on, and clarify anything that any of the answers that you're trying to get and you haven't been able to, all right, or you're not understanding how to solve it at all. Okay. All right. So while you're doing that, as I say, feel free to email me things if you got stuck. I'll bring it up in class, or I could respond if it's something that looks like it's a general thing that everybody might be interested in. I'll respond to everyone with it. If it's just a minor thing where you might have made some little mathematical error and so on, then I'll just respond to you. Okay, but it's up to you now. It's now my part for summer, for all intents and purposes, is now finished. It is really you to sit down and go through the material and tell me what you still need clarification on, or what you don't need clarification on, and that kind of thing. It's practice. We have enough past papers. You still have the problem sets from last time with the solutions too, so you can do over those sets without looking at the answer. So try to get the answer. As I mentioned before, now that you're doing the sets now, it's a try to see how far you get along by doing the problem in the time that you have. So you have 3 hours to do 5 questions. So you have what, about 35 minutes, 35, 36 minutes kind of thing to do a question. So see how far you get in the 35 minutes. See where you get into this in it. Stop and then check your answer against the one in the solutions. See where you where you fell short, and then go forward. As I mentioned, the more working you show me, the better off you are. So like, for instance, in this one, in this particular question here, you're substituting. So don't do everything in one step. So you go from step 1 will be to find the Z transform of the entire equation. So you write it down properly, including all the things that have to be substituted. Then you make the substitutions for the initial conditions. Then you start to simply group and simplify. And every time you write down that, if you get that step correct, you basically like have a mark per line going through. Getting the correct substitution for UKT is another mark. And then when you simplify and you get the expression, if you get the answer in the unsimplified form, at that point in time, you already have like about 7 or 10 marks there. So if at that point, the 35 minutes ran out, move on to the other part, because if you were correct up to that point, you have 7 out of 10 marks. In other words, you have 70% of the marks in hand there. Move on to part B. Same sort of thing. In this one, I have given you something here. The thing has 3 poles. I've given you 1, so you have to find the other 2 poles. Then when you have to find the other 2 poles, to find the inverse transform means that you have to have do some partial fractions and so on. So again, if you look at this, I've given you 1 pole. You have to find 2 more poles, right? Now it's 10 marks for the question, right? So the other 2 poles, 2 marks each. So sorry, 1 mark each. So 2 marks for that. So when you get that now, you have to break this up into partial fractions. So you have to factorize it properly. So that is 1. So you have 3 marks here. If you have 3 factors, because it's 3 poles, so you're going to have 3, when you break it up into partial fractions, you're going to have 3 things to solve the coefficients for A, B, and C. So that's another 3 marks there. So that's 6 marks by the time you have A, B, and C. And then the closed form solution now is to go to the Z transform tables. And for each of those now, you pull out the correct inverse Z transform and write down the final answer, right? So if the 30 minutes or 35 minutes run out at the point when you evaluated the 3 coefficients, then at that point in time, you have 6 of the 10 marks in there. The rest is for looking up in the tables and so on, right? So if at the first time you try it, at the end of 30 minutes, you got an unsimplified answer for part A, and you got as far as the coefficients for part B, right? You have in all 13 out of the 20 marks for the problem there, which is over half. So you already passed the question, if you like. So the next thing now is to see how much more I could get, right? So the next time you do the question, you try to get more done in the same time. But as I said, the more steps you show me, the more marks I am able to see. And if you make a mistake early on, so let's say for this one here, that somehow you calculate the incorrect roots, but then you do the entire rest of the problem correct. As I say, you have 1 mark per pole for this question. I've given you 1, you have 2 other poles to get. If you get both of them wrong, but you get everything else based on your answer, you get the whole rest of the question correct, you have 8 marks, right? I'll penalize you for not getting not solving the thing the first time, but I will recalculate your answer based on what you have. So you're still getting 8 marks, all right? So the thing is, I'm more interested to see that you know what the steps are and that you're able to at least demonstrate to me that you understand the material good enough to pass the question and pass the course. All right? Everything else after that now is bonus. Okay? Fair enough? Yes, no, maybe. Right. So up to you now. Okay. So in your hands at this point in time. So between now and Friday, let me know what it is. We have the class time set aside, but I have no more teaching to do for you all. I've covered the material, so it is really to sort of clarify any issues that you may be having at this point. Okay? All right, guys. So, well, thank you for attending. And I'll post up the recording for this. And as I say, it's now up to you. Right? You have your homework and your revision to do. And let me know. I have no teaching in the classes at this point, but as the questions come in, if you depending on what you want, then I'll take it from there. All right. Okay. So well, I'll see some of you all in another hour or so for the electronics course, which is pretty much the same thing at this point in time. All right. Let me stop the recording.